Hello there. Tonight, you are about to leave the familiar. Not with force, not with urgency, but with a quiet step into the vast unknown beyond Earth. Beyond the sun, beyond the planets you know, there are worlds drifting in silence. Planets that burn under endless fire. Planets wrapped in oceans deeper than imagination, and others wandering alone through eternal darkness. They do not call out. They do not shine for attention. And yet, they exist. Billions of them, each one moving with precision, with purpose, with a calm that feels almost intimidating. A reminder that the universe does not rush, does not hesitate. It simply continues. And tonight, you will drift among them. Slowly, gently, one thought at a time, discovering truths that feel distant, yet strangely close, as if they have always been waiting for you to notice. So before we begin, take a quiet moment. If you find comfort here, if this calm pulls you in, then subscribe to the channel and leave a like on this video. Not out of habit, but as a quiet signal that you want more of these journeys, more of this stillness, more of this endless exploration. Now, let your breathing slow. Let the noise of the world fade away, and allow yourself to drift, because out there, in the silent dark between the stars, the universe is already waiting, and it has been for a very long time. Chapter 1. The Silent Discovery of Worlds Beyond Our Sun. Hello there. Tonight, as you settle into stillness, allow your mind to drift gently beyond the familiar glow of our sun, beyond the comforting boundaries of our solar system, into a vast and quiet ocean of stars. For most of human history, the idea of planets orbiting other stars was nothing more than a quiet speculation, a philosophical whisper carried through centuries. Ancient thinkers wondered, if our sun hosts planets, could other stars do the same? But the universe kept its secrets well hidden, silent, distant, and impossibly vast. The first truth about exoplanets is this: for thousands of years, we had absolutely no proof they existed. Not because they were rare, but because they were incredibly difficult to see. Planets do not shine like stars. They reflect faint light, often lost in the overwhelming brilliance of their parent stars. Imagine trying to spot a tiny firefly drifting beside a powerful lighthouse from thousands of kilometers away. That is the challenge astronomers faced. And yet, curiosity persisted. In 1992, something remarkable happened. Astronomers discovered the first confirmed planets beyond our solar system. But these were not orbiting a normal star. Instead, they circled a pulsar, the dense, spinning remains of a dead star. These worlds were unlike anything imagined before. Harsh, irradiated, and bathed in intense radiation. It was a strange beginning, almost unsettling. The first known exoplanets were not peaceful Earth-like havens, but remnants of cosmic violence. Just a few years later, in 1995, a more familiar kind of discovery emerged. A planet was found orbiting a sun-like star. This world, known as 51 Pegasi b, changed everything. It was the first time humanity confirmed that a planet existed around a star similar to our own. But here is the second truth. It was nothing like what we expected. 51 Pegasi b was a hot Jupiter, a massive gas giant orbiting extremely close to its star. So close, in fact, that it completes an orbit in just about 4 days. This shattered earlier assumptions. Scientists had believed that gas giants could only form far from their stars, like Jupiter in our solar system. But here was a giant planet, hugging its star in a tight, scorching embrace. Some planets orbit their stars in just hours. Others take centuries. Some are larger than Jupiter, others smaller than Earth. There are planets so hot that their surfaces glow like molten metal, and others so cold they drift in eternal darkness. But how do we find them? This leads to another gentle truth. We rarely see exoplanets directly. Instead, we observe their subtle effects. One common method is called the transit method. When a planet passes in front of its star, it causes a tiny dip in the star's brightness. This dip is incredibly small, often less than 1%, but sensitive instruments can detect it. Imagine watching a distant candle flicker ever so slightly, not because the flame changed, but because something passed quietly in front of it. That is how we glimpse these hidden worlds. Another method involves detecting the wobble of a star. Planets exert a gravitational pull on their stars, causing them to move ever so slightly. This movement can be measured through shifts in the star's light. It is a delicate dance, a subtle interaction between star and planet, revealing the presence of something unseen. And here is something quietly fascinating. Most of the exoplanets we've discovered are not like the planets in our own solar system. Our system, with its neat arrangement of rocky inner planets and gas giants farther out, may not be the cosmic norm. Instead, the universe seems to delight in variety, in unexpected configurations, in worlds that challenge our understanding. There are planets with orbits tilted at extreme angles, planets orbiting two stars, planets that may be made largely of water, and even planets where it might rain molten glass sideways due to intense winds. As discoveries continued, missions like the Kepler Space Telescope revolutionized our understanding. Kepler stared at a small patch of sky for years, patiently watching, waiting for those tiny dips in starlight, confirmed that our galaxy, the Milky Way, likely contains billions of planets. Billions. Pause for a moment and let that settle in. Every star you see in the night sky, and countless more you cannot see, may host its own system of worlds. Some may be barren and silent. Others may be dynamic and strange. And somewhere, perhaps, there could be planets with conditions just right for life. But even with all this progress, we are still at the beginning. Our instruments are improving, our methods becoming more refined, but the universe remains vast and full of quiet mysteries. There is also a humbling truth in all of this. We are discovering these distant worlds not by traveling to them, but by observing faint signals across unimaginable distances. Light that has traveled for years, sometimes centuries, reaches us carrying subtle clues about planets we will never physically touch. And yet, through patience and ingenuity, we are learning their stories. As you rest, imagine these distant systems, stars glowing softly in the dark, each one surrounded by its own collection of worlds, some familiar, others beyond imagination. The universe is not empty. It is filled with quiet complexity, with hidden planets drifting in silent orbits, each one a small piece of a much larger cosmic story. And tonight, you are gently exploring them, one thought at a time. As your thoughts continue to drift outward, beyond the quiet edges of our solar system, there is another gentle truth waiting to unfold. Not all discoveries of exoplanets come from grand, dramatic moments. Many arrive quietly, almost unnoticed at first, hidden within streams of data. Astronomers often spend years analyzing faint signals, carefully separating real planetary signatures from noise, interference, and cosmic distractions. It is a patient kind of exploration, one that rewards stillness and precision rather than speed. Which leads to another fascinating truth. Not all planets belong to stars. There exist rogue planets, worlds that drift freely through the galaxy, untethered to any star. These planets may have been ejected from their original systems during gravitational interactions. Alone in the darkness, they travel through interstellar space, carrying whatever atmosphere or heat they once had. Some scientists believe there could be billions of these wandering planets in our galaxy alone. Imagine that, silent worlds, moving through the void, unseen, unlit, yet still part of the grand cosmic story. As our tools have improved, so too has our ability to directly image certain exoplanets. While most remain too faint and too close to their stars to be seen directly, a few have been captured as tiny points of light. These images are not detailed landscapes, but they are real, direct glimpses of distant worlds. Each one represents a profound achievement, capturing the faint glow of a planet across vast cosmic distances. There is also a growing effort to find Earth-like planets, worlds that are similar in size and orbit within the habitable zone of their stars. This is the region where temperatures might allow liquid water to exist on the surface. But here is an important truth. Being in the habitable zone does not guarantee life. Many factors come into play: atmosphere, magnetic fields, geological activity, and more. Still, the discovery of such planets brings a quiet sense of possibility. Perhaps somewhere, under an alien sky, oceans ripple gently, winds move across unfamiliar landscapes, and conditions exist that echo the delicate balance we know on Earth. As you continue to relax, consider how much we have learned in such a short time. Just a few decades ago, exoplanets were purely theoretical. Now they are a central part of modern astronomy. And yet, for all we have discovered, we have only just begun. There are still countless stars to study, countless signals to interpret, countless worlds waiting quietly in the darkness. Each new discovery adds another piece to the puzzle, another glimpse into the diversity of the universe. And perhaps the most calming truth of all is that the universe does not rush. These planets have been there for billions of years, orbiting silently, long before we knew how to look for them. They will continue their gentle motion, whether observed or not. But tonight, as you drift closer to rest, you have already traveled far. Far beyond Earth, beyond the sun, into a universe filled with hidden worlds. And somewhere out there, among the countless stars, the story continues, quietly, endlessly, and beautifully. Chapter 2: Strange Giants and Burning Skies. As your mind drifts a little deeper into the quiet vastness of space, we now move towards some of the most extraordinary worlds ever discovered, planets that do not resemble Earth in any comforting way, but instead reveal just how creative the universe can be. The first truth to gently settle into is this: many of the earliest exoplanets we discovered were enormous, far larger than Earth, and often even larger than Jupiter. These are known as gas giants, but unlike the calm, distant giant in our own solar system, many of these worlds exist in extreme environments. Some orbit so close to their stars that their atmospheres are stretched, heated, and constantly reshaped by intense radiation. One of the most fascinating categories among these is the hot Jupiter. These planets are massive, similar in size to Jupiter, but orbit incredibly close to their stars. Because of this, their temperatures can rise to thousands of degrees Celsius, hot enough to melt metals. Imagine a sky where the air itself glows faintly, where heat is not something you feel, but something that surrounds everything completely. On some of these planets, winds rage at unimaginable speeds. Instead of gentle breezes, or even storms like those on Earth, these worlds experience winds that can exceed 5,000 kilometers per hour. These winds carry clouds made not of water, but of vaporized rock and metals. And here comes another quiet but astonishing truth. On certain hot Jupiters, it may actually rain molten glass. Because of the extreme temperatures, materials like silicates can vaporize into the atmosphere. As they cool slightly, they condense into tiny particles, forming clouds. Then, driven by powerful winds, these particles can fall as rain, sharp, glowing droplets of glass moving sideways through the atmosphere. It is difficult to fully imagine, but also strangely beautiful in its own way. Another truth reveals itself when we consider how these giant planets behave under such intense heat. Many of them become inflated. Their atmospheres expand due to the heat, making them much larger in size than expected for their mass. Some of these planets are so puffed up that they are less dense than foam, meaning they could theoretically float on water, if such a vast ocean could exist. This leads to another surprising realization. Size does not always mean heaviness. A planet can be enormous, yet incredibly light, its atmosphere stretched thin by the relentless energy of its nearby star. There are also gas giants that orbit their stars in incredibly short periods. Some complete a full orbit in less than a single Earth day. This means their year is shorter than our day. Imagine watching a sunrise, and before you've had time to rest, the sun has already set and risen again. Time itself feels different on such worlds. Another fascinating truth is that many hot Jupiters are tidally locked. One side constantly faces the star, absorbing intense heat, while the other side remains in perpetual darkness. The temperature difference between these two sides can be extreme, thousands of degrees apart. This creates a dynamic atmosphere where heat is constantly being redistributed. Winds rush from the hot side to the cold side, attempting to balance the difference, but never quite succeeding. The result is a planet in constant motion, a world where the atmosphere never rests. Some of these planets even have glowing atmospheres that emit light due to their high temperatures. Instead of simply reflecting starlight, they can shine faintly on their own, like distant embers drifting in the darkness of space. Another quiet truth emerges when we consider their formation. Scientists believe that many of these giant planets did not originally form so close to their stars. Instead, they likely formed farther away, where temperatures were lower, and then gradually migrated inward over time. This journey inward would have been slow, but powerful, reshaping the planetary system as it happened. Smaller planets may have been pushed aside, or even ejected entirely, leaving behind a system dominated by a single massive giant. And yet, not all giant exoplanets are hot. Some exist far from their stars, in regions of deep cold and darkness. These planets may resemble Jupiter or Saturn more closely, with thick atmospheres and swirling storms, but without the intense heat of close proximity. Another fascinating truth is that some gas giants may have cores much larger than Jupiter's, or in some cases, no solid core at all. Their internal structures remain a mystery, hidden beneath layers of dense gas and pressure. The deeper you go into such a planet, the more intense the conditions become. Pressure increases, temperatures rise, and matter behaves in ways that are difficult to fully understand. In some models, hydrogen within these planets may exist in a metallic state, conducting electricity and contributing to powerful magnetic fields. These magnetic fields can be enormous, extending far into space, interacting with stellar winds and creating vast regions of charged particles. And here is another quiet but powerful truth. These giant planets are not just passive objects. They actively shape their environments. Their gravity influences nearby bodies, their magnetic fields interact with space, and their presence can determine the structure of entire planetary systems. As you continue to relax, imagine these massive worlds drifting close to their stars, their atmospheres glowing, winds rushing endlessly, skies filled with unfamiliar clouds. They are not peaceful like Earth, but they are not chaotic either. They exist in a kind of balance, a steady rhythm of heat, motion, and gravity. Each one is a reminder that the universe does not follow a single pattern, but instead explores every possibility. And tonight, as your thoughts move gently through this cosmic landscape, you are beginning to understand just how vast and how varied these distant worlds truly are. As your awareness continues to drift across these immense and glowing worlds, there is still more to quietly uncover about these strange giants, planets that challenge not only our expectations, but also our imagination. Another gentle truth begins with color, something we rarely think about when imagining distant planets. Many hot Jupiters are not the soft browns or pale yellows we might expect, but instead display deep, unusual shades. Some appear intensely dark, almost as black as charcoal, absorbing nearly all the light that reaches them. Others glow with hints of blue, not because of oceans like Earth, but due to the scattering of light by silicate particles in their atmospheres. Imagine a planet the color of midnight, orbiting so close to its star that its surface temperature could melt iron, yet reflecting almost no light at all. It would be nearly invisible against the darkness of space, a silent, heated shadow. And then, there are planets that reflect surprisingly little light despite being so close to their stars. One such example absorbs most of the starlight that falls upon it, making it darker than coal. This happens because of the absence of reflective clouds and the presence of light-absorbing elements in its atmosphere. It is a quiet reminder that brightness does not always come from proximity. Another truth unfolds when we consider the chemistry of these alien skies. Unlike Earth's atmosphere, which is dominated by nitrogen and oxygen, many gas giants are filled with hydrogen and helium, along with traces of exotic compounds. In extreme heat, molecules behave differently. They break apart, recombine, and form unexpected structures. Some atmospheres contain vaporized metals like iron and titanium. In certain temperature ranges, these metals can condense and fall as rain, not in liquid form like water, but as molten droplets. This creates a cycle similar to Earth's water cycle, but composed of entirely different materials. There are also planets where clouds may be made of aluminum oxide, essentially the same material as sapphire and ruby. Under the right conditions, these clouds could form and drift through the atmosphere, glowing faintly under the intense light of their star. It is a strange and beautiful thought. Clouds made of gemstones, floating in skies too hot for anything familiar to survive. Another fascinating truth is that some of these giant planets lose their atmospheres over time. The intense radiation from their stars can strip away the outer layers of gas, causing the planet to slowly evaporate. This process can create long tails of gas trailing behind the planet, similar to the tail of a comet. These evaporating planets are in a constant state of change, gradually shrinking over millions or billions of years. What begins as a massive gas giant could eventually be reduced to a much smaller core, or disappear entirely. Time, in this sense, is quietly reshaping these worlds, one particle at a time. There are also gas giants that orbit very young stars. In these systems, the planets are still forming, still gathering material from the surrounding disk of gas and dust. Observing these systems gives scientists a glimpse into the early stages of planetary formation, a process that once shaped our own solar system long ago. Another truth to consider is the role of gravity in shaping these giants. Because of their immense mass, gas giants exert strong gravitational forces, not only on nearby planets, but also on their stars. In some cases, the gravitational interaction between a planet and its star can cause tidal effects, slightly stretching the star or altering its rotation. This relationship is not one-sided. Just as the planet influences the star also influences the planet, creating a continuous exchange of energy and motion. Some gas giants also have moons, though detecting them is extremely difficult. These moons, often referred to as exomoons, remain largely hypothetical, but there is growing evidence that they may exist. If they do, some could be large enough to have their own atmospheres, and perhaps even conditions suitable for liquid water. Imagine a massive gas giant dominating the sky, with a moon orbiting it, a world illuminated not only by its star, but also by the reflected glow of its parent planet. It is a quiet and distant possibility, but one that expands the idea of where life might exist. Another truth lies in the temperature differences within these planets. While their outer atmospheres may be incredibly hot, deeper layers can behave in complex ways. Heat flows inward and outward, a pressure builds, and materials transition between different states. These internal dynamics can generate powerful storms, similar in concept to Jupiter's Great Red Spot, but potentially even more intense. Some storms on exoplanets may last for centuries, swirling endlessly in thick, turbulent atmospheres. And yet, despite all this activity, there is a kind of stillness to these worlds when viewed from afar. They orbit their stars in steady paths, following the same gravitational rules that govern everything in the universe. Another fascinating truth is that some gas giants emit more heat than they receive from their stars. This is due to leftover energy from their formation, slowly radiating outward over time. Even without strong stellar heating, these planets can remain warm, glowing faintly in infrared light. It is a quiet reminder that not all planetary energy comes from stars. Some comes from within. As technology continues to improve, scientists are beginning to study these planets in greater detail. New telescopes allow for more precise measurements, better analysis of atmospheres, and even the ability to map temperature differences across a planet's surface. Each new observation adds depth to our understanding, turning distant points of light into complex, dynamic worlds. And yet, for all we know, there is still so much we do not understand. These strange giants, with their burning skies and shifting atmospheres, are only one part of the broader story of exoplanets. They are the easiest to detect, the most dramatic to observe, but not necessarily the most common. As you continue to relax, let your thoughts settle on these immense worlds, glowing softly in the darkness, their storms raging quietly, their skies filled with unfamiliar clouds. They are distant, unreachable, yet deeply connected to the same universe we inhabit. And in their silent orbits, they remind us that the cosmos is far more varied, far more imaginative than we once believed. Chapter 3. Super-Earths and Ocean Worlds. As your thoughts continue to drift gently through the vastness of space, We now move away from the towering giants and toward something a little closer to home, yet still wonderfully unfamiliar. There exists a class of planets known as super-Earths, and despite the name, they are not simply larger versions of our world. This is the first quiet truth to understand. A super-Earth is defined only by its size and mass, typically between 1 and 10 times the mass of Earth, but beyond that, they can be incredibly diverse. Some may be rocky with solid surfaces and mountains. Others may be covered in deep oceans or wrapped in thick atmospheres of gas. And some may be something entirely different, worlds that do not fit neatly into any category we recognize. The universe does not copy Earth. It experiments. One of the most fascinating truths is that super-Earths are among the most common types of planets in our galaxy. While our own solar system has none, many other systems are filled with them. This suggests that our planetary arrangement may not be typical, and that Earth-like worlds, in the strictest sense, might be rarer than we once assumed. And yet, super-Earths still offer something deeply intriguing: the possibility of familiar conditions, just scaled differently. Imagine standing on a planet twice the size of Earth. Gravity would be stronger, your weight heavier, your movements slower. Mountains might be shorter and broader due to the increased gravitational pull, and the atmosphere could be thicker, holding on to gases more effectively. Another gentle truth is that some super-Earths may have atmospheres rich in hydrogen, making them more like mini-gas giants, while others may have thinner, Earth-like atmospheres. The line between rocky planet and gas planet becomes blurred in this size range. And then, there are the ocean worlds. These are planets believed to be covered almost entirely by water, with little to no land. But these are not oceans like the ones we know. On some of these planets, the oceans could be hundreds of kilometers deep, far deeper than anything on Earth. At such depths, the pressure becomes immense. Water behaves differently, forming exotic phases of ice even at high temperatures. Deep beneath the surface, there may exist layers of supercritical water, a state where liquid and gas are no longer distinct. It is a strange, quiet world where the familiar becomes something entirely new. Another truth to gently consider is how these ocean worlds might form. Some may originate in colder regions of their systems, where ice is abundant, and then migrate inward toward their stars. As they warm, the ice melts, creating vast global oceans. Others may form with a mixture of rock and water from the very beginning, never developing large landmasses at all. And here is something quietly profound. On such planets, there may be no continents, no beaches, no solid ground exposed to the air. The entire surface could be an endless ocean, stretching uninterrupted across the globe. Imagine drifting on such a world, surrounded by water in every direction, beneath a sky that may look entirely different from our own. Another fascinating truth is that some super-Earths may have active geology, much like Earth. Plate tectonics, volcanic activity, and shifting crusts could all exist, depending on the planet's composition and internal heat. This geological activity could play an important role in regulating the planet's atmosphere, cycling gases like carbon dioxide and maintaining long-term stability. On Earth, this process has helped sustain life for billions of years. Whether similar processes occur on super-Earths remains an open question, but it is one that scientists continue to explore with quiet curiosity. There are also super-Earths that orbit very close to their stars, becoming intensely hot. These are sometimes referred to as lava worlds. On these planets, the surface may be partially or entirely molten, with rivers of lava flowing across the landscape. The heat can be so extreme that rock itself vaporizes, forming a thin atmosphere of vaporized minerals. As this vapor cools, it may condense and fall back to the surface, creating a kind of rock cycle in the sky. It is a slow, continuous transformation shaped by heat and gravity. Another truth emerges when we consider rotation. Some super-Earths may rotate very slowly, or be tidally locked with one side always facing their star. This creates a permanent day side and night side, with a narrow region in between where temperatures might be more moderate. This terminator zone could, in theory, be one of the most stable regions on such a planet, a place where conditions are neither too hot nor too cold. It is a quiet band of balance, circling a world of extremes. There are also super-Earths with thick, dense atmospheres that trap heat efficiently. These planets may experience a runaway greenhouse effect, similar to Venus, but on a larger scale. Surface temperatures could become incredibly high, making them inhospitable despite being in the so-called habitable zone. This reminds us of another important truth. Location alone does not determine habitability. A planet's atmosphere, composition, and history all play crucial roles. And yet, among these many variations, there are some super-Earths that sit in just the right place with conditions that may allow liquid water to exist, and temperatures that are not too extreme. These planets capture our imagination, not because we know they are like Earth, but because they might be. Another gentle realization is that studying super-Earths helps us understand our own planet more deeply. By comparing different worlds, we learn what makes Earth unique, and what factors are necessary for stability and life. Each super-Earth is like a natural experiment, testing different combinations of size, composition, and environment. As you continue to relax, imagine these worlds, some covered in deep oceans, others glowing with molten rock, others wrapped in thick, mysterious atmospheres. They are not copies of Earth, but they are not entirely alien either. They exist somewhere in between, familiar enough to imagine, yet different enough to surprise. And in their quiet orbits, they remind us that the universe is full of possibilities, waiting patiently to be understood. As your awareness continues to float gently among these distant, water-covered and stone-heavy worlds, there is still more to quietly uncover about their nature, their possibilities, and their quiet mysteries. Another truth begins with pressure, something we rarely feel deeply on Earth, yet something that defines the nature of many super-Earths and ocean worlds. On a planet larger than Earth, gravity presses down more strongly. This means that not only is the surface heavier, but everything beneath it is compressed more tightly. In ocean worlds, this pressure becomes especially significant. As you descend into these vast global oceans, the weight of the water above increases dramatically. On Earth, the deepest point, the Mariana Trench, reaches about 11 kilometers. But on some exoplanet ocean worlds, the depth could extend beyond 100 kilometers, or even more. At such depths, water no longer behaves in familiar ways. Instead of remaining liquid, it transforms into exotic forms of ice. Even though temperatures may still be relatively high, these are known as high-pressure ice phases, such as Ice 6 or Ice 7. Unlike the ice we know, these forms are dense and compact, forming solid layers beneath the ocean. This creates a layered structure: a surface ocean, then deep high-pressure ice, and beneath that, perhaps a rocky core. And here comes a quiet but important realization. If this layer of high-pressure ice separates the ocean from the rocky core, it may limit the exchange of minerals and heat. On Earth, interactions between water and rock, such as hydrothermal vents, play a key role in supporting life. On these ocean worlds, that connection might be absent. And yet, the universe often finds ways to surprise us. Another fascinating truth is that not all ocean worlds are entirely covered in water forever. Some may have subtle variations in surface conditions, perhaps small regions where land briefly emerges, or areas where the ocean is thinner. These variations could create localized environments, each with its own unique balance of temperature and chemistry. Even on a seemingly uniform world, diversity may still exist. There are also super-Earths that may have thick hydrogen-rich atmospheres overlaying deep oceans. In such cases, the atmosphere itself can act as insulation, trapping heat and maintaining stable temperatures even far from the star. These planets may exist outside the traditional habitable zone, yet still possess liquid water beneath their skies. It is a gentle reminder that habitability is not confined to a narrow region, but can emerge under a range of conditions. Another truth lies in the way light behaves on ocean worlds. If the atmosphere is thick or hazy, sunlight reaching the surface may be dim and diffused. The sky could appear softly glowing with muted colors, rather than the bright blue we know on Earth. Beneath the ocean surface, light would fade quickly, giving way to darkness at relatively shallow depths. Yet, even in darkness, there may be movement, currents flowing slowly, driven by heat and rotation. These worlds may feel quiet, but they are not still. Another fascinating aspect is the possibility of waves. With global oceans and potentially strong winds, some ocean worlds could experience waves far larger than anything on Earth. Without continents to break their motion, waves could travel vast distances uninterrupted, building in size and energy. Imagine standing, if you could, on a floating platform in such an ocean, watching waves rise and fall endlessly under an unfamiliar sky. And yet, there is also the possibility of calm. On some planets, if winds are weak or atmospheres are stable, the ocean surface could be remarkably smooth, reflecting the sky like a mirror, stretching endlessly in all directions. Another quiet truth is that super-Earths may retain heat more effectively than smaller planets. Their larger size means more internal heat from formation and radioactive decay. This could sustain geological activity for longer periods, potentially supporting magnetic fields and dynamic interiors. A magnetic field, in turn, can protect a planet's atmosphere from being stripped away by stellar winds, preserving the conditions necessary for long-term stability. This interplay between size, heat, and protection is subtle, but deeply important. There are also super-Earths that orbit small, cool stars known as red dwarfs. These stars are abundant in our galaxy, and many of the potentially habitable planets discovered so far orbit them. However, red dwarfs can be active, emitting flares and radiation that may affect the atmospheres of nearby planets. Some super-Earths may have adapted to these conditions, with thick atmospheres or magnetic fields providing protection. Others may have lost their atmospheres entirely, leaving behind barren surfaces. It is a delicate balance shaped by both the planet and its star. Another truth emerges when we consider time. Many of these planets have existed for billions of years, far longer than human history, far longer than life on Earth has been aware of itself. During this time, their conditions may have changed dramatically. Oceans may have formed, evaporated, or frozen. Atmospheres may have thickened, thinned, or transformed completely. Planets are not static. They evolve slowly, quietly, over immense stretches of time. And here is something deeply calming. Even in their differences, these worlds follow the same fundamental laws as Earth. Gravity, chemistry, thermodynamics, all the same principles apply. The universe is consistent, even as it creates endless variation. Another fascinating truth is that scientists are beginning to model what the surfaces of these planets might look like. While we cannot see them directly in detail, simulations allow us to imagine their landscapes, their oceans, their skies. These models suggest worlds that are both alien and familiar, places where waves move, clouds drift, and light changes with time. And perhaps, somewhere among these countless super-Earths and ocean worlds, there may exist conditions that allow life to emerge. Not necessarily life as we know it, but something that uses the same building blocks shaped by different environments. It is a quiet possibility, one that does not demand certainty, only openness. As you continue to relax, let your thoughts settle on these vast ocean planets, their deep waters, their hidden layers, their quiet, endless horizons. They are not loud or dramatic, but they are full of depth, both literally and figuratively. And in their stillness, they invite you to drift, to imagine, and to rest within the gentle realization that the universe holds far more than we can ever fully explore. Chapter 4. Rogue Planets Drifting in Darkness. As your thoughts continue to drift gently outward, beyond stars, beyond warmth, beyond familiar orbits, we now enter one of the quietest and most mysterious realms of all. These are the worlds that do not belong. The first truth to settle into is both simple and deeply unsettling. Not all planets orbit stars. Some wander alone through the galaxy, untethered, unlit, and almost completely invisible. These are known as rogue planets. Unlike Earth, which moves in a steady path around the Sun, or even the distant exoplanets we've already explored, rogue planets travel freely through space. They are not bound to any star's gravity. Instead, they drift slowly through the vast darkness between stellar systems. And yet, they are not rare. In fact, some scientists believe there could be as many rogue planets as there are stars in our galaxy, perhaps even more. Pause for a moment and imagine that, for every star you see in the night sky, there may be a silent planet wandering alone, unseen, unilluminated, and entirely independent. Another gentle truth is how these planets come to exist. Most rogue planets were not always alone. Many likely formed within planetary systems, just like Earth. But over time, gravitational interactions can become unstable. Large planets pull on smaller ones. Stars shift, or nearby stellar encounters disturb the balance. Eventually, a planet may be flung outward, escaping the gravitational hold of its star. This process is not sudden in human terms, but over cosmic timescales it is inevitable. And once a planet is ejected, there is no return. It begins a quiet journey through interstellar space, a journey that may last billions of years. Another fascinating truth is that rogue planets are incredibly difficult to detect. Without a star to illuminate them, they emit very little visible light. They do not reflect sunlight, and they do not pass in front of a star to create detectable signals. Instead, astronomers rely on subtle techniques, such as gravitational microlensing. When a rogue planet passes in front of a distant star, its gravity bends the light of that star, causing a brief increase in brightness. This effect is fleeting, lasting only hours or days, but it reveals the presence of an otherwise invisible world. It is like noticing a ripple in a distant reflection and realizing something unseen has passed between. Another quiet truth is that some rogue planets may still retain heat, not from a star, but from their own formation. When planets form, they generate internal heat through gravitational compression and radioactive decay. For large planets, especially gas giants, this heat can persist for long periods. Even without a star, they may glow faintly in infrared light, slowly releasing energy into the cold of space. And here is something deeply intriguing. Some rogue planets may not be entirely frozen. If a planet has a thick atmosphere, particularly one rich in hydrogen, it could trap internal heat effectively. This insulation might allow temperatures at the surface or beneath it to remain relatively stable. In such cases, there could even be liquid water hidden beneath layers of ice or atmosphere. Imagine a world drifting through darkness, with no sun, no sunrise or sunset, yet deep beneath its surface, an ocean remains warm and quiet. It is a subtle, almost hidden form of possibility. Another truth emerges when we consider scale. Rogue planets can range in size from small, rocky bodies to massive gas giants. Some may be similar to Earth, while others may rival Jupiter in size. Their diversity is just as vast as that of planets bound to stars, perhaps even more so. There are also rogue planets that may have been ejected very early in their formation, before they fully developed. These worlds could be incomplete, with unusual compositions or structures. Others may have formed independently, not around stars at all, but directly from collapsing clouds of gas and dust. These objects blur the line between planets and stars, existing somewhere in between. Another fascinating truth is the sheer isolation of these worlds. Without a star, there is no consistent source of light. The sky would be almost completely dark, save for distant stars appearing as faint, unmoving points. There would be no day, no night, only a continuous, silent darkness. Time in such a place would feel different. Without the rhythm of a rising and setting sun, there is no natural cycle to mark the passage of time. Only the slow, steady drift through space. And yet, even in this isolation, rogue planets are still part of the galaxy. They move through gravitational fields, occasionally passing near stars or other planets, though such encounters are rare. For the most part, they remain alone. Another quiet truth is that some rogue planets may carry remnants of their past systems. They may have moons or rings, or traces of atmospheres shaped by earlier conditions. These features persist, even after the planet has left its original home. It is as if the planet carries a memory of where it once belonged. There is also the possibility, however distant, that life could exist on a rogue planet. Not life powered by sunlight, but perhaps by internal heat, chemical reactions, or geothermal activity. On Earth, life exists in deep ocean vents far from sunlight, sustained by energy from within the planet. If similar conditions exist on a rogue planet, life might find a way. It would be quiet, hidden, and entirely different from what we know. But it is not impossible. As you continue to relax, imagine these wandering worlds, drifting slowly through the galaxy, untouched by starlight, wrapped in silence. They are not chaotic or violent, but calm, steady, and deeply isolated. Each one follows its own path, shaped only by gravity and time. And in their quiet journey, they remind us that not all worlds need a star to exist. Some simply continue. As your thoughts continue to drift through the quiet emptiness between the stars, we remain with these solitary worlds, the wanderers of the galaxy, moving slowly through a darkness that never truly changes. Another gentle truth begins with motion. Rogue planets are not stationary. They are always traveling. Once ejected from their original systems, they continue forward, guided only by gravity and inertia. Their paths may curve slightly as they pass through the gravitational influence of stars or dense regions of the galaxy, but for the most part, they follow long, quiet trajectories through open space. Their speed can vary. Some drift slowly, while others move at tens of kilometers per second. Yet even at these speeds, space is so vast that encounters with other objects are incredibly rare. A rogue planet may travel for millions of years without coming close to another star. It is a journey defined not by events, but by the absence of them. Another fascinating truth is that temperature on rogue planets depends almost entirely on internal heat. Without a nearby star, surface temperatures can drop to extremely low levels, often hundreds of degrees below freezing. The outer layers of these planets, if they are rocky, may become solid and still frozen in place for billions of years. But beneath the surface, things may be very different. If the planet retains enough internal heat, subsurface layers could remain warm. In some cases, thick ice layers may act as insulation, trapping heat below. Beneath these icy shells, there could be liquid water oceans, slowly circulating in darkness. These hidden oceans would never see sunlight, yet they may still move, shaped by geothermal energy rising from the planet's core. It is a quiet and almost secret world, hidden beneath frozen stillness. Another truth to consider is that some rogue planets may have atmospheres that freeze and collapse onto the surface. Without heat from a star, gases like carbon dioxide or nitrogen can condense into solid form, forming layers of frost or ice. Over time, the atmosphere may become extremely thin or disappear entirely, leaving behind a bare and silent surface. Yet, in some cases, particularly for larger planets, a gravity may be strong enough to hold onto a thick atmosphere. If this atmosphere is dense and insulating, it could help retain heat, preventing the planet from becoming completely frozen. This delicate balance between gravity and temperature determines whether a rogue planet becomes a frozen wasteland or a more complex, layered world. Another quiet truth is the absence of weather as we know it. Without sunlight to drive atmospheric circulation, traditional weather systems, like winds, storms, and clouds, may be minimal or non-existent. However, if internal heat escapes unevenly, it could create localized movement in the atmosphere or beneath the surface. Subtle flows, slow currents, small shifts over long periods of time. Nothing sudden, nothing dramatic, just gradual change. There are also rogue gas giants, massive planets composed mostly of hydrogen and helium. These worlds may retain significant internal heat, allowing them to remain relatively warm compared to their surroundings. Some of these giants may even emit more heat than they receive, which in this case is none at all. Their warmth comes entirely from within, slowly radiating outward into the cold vacuum. In infrared wavelengths, these planets may glow faintly, like distant embers, barely visible against the darkness. Another fascinating truth is that rogue planets may occasionally pass near other star systems. While the probability is low, over billions of years such encounters can happen. If a rogue planet passes close enough to a star, it may be captured by gravity, becoming part of a new system. Alternatively, it may simply pass through, its path slightly altered, continuing onward into the void. These rare interactions add a subtle unpredictability to their journeys. Small changes in direction, gentle shifts in motion. Another quiet realization is that rogue planets experience no sunrise, no sunset, no changing sky. The stars in their sky would remain fixed, unchanging, distant points of light that never move relative to the planet's surface. Without a central star, there is no dominant source of light to define direction or time. The concept of a day loses meaning. Time becomes something internal, measured not by light, but by slow processes, cooling, shifting, evolving. Another truth lies in the idea of sound, or rather, the absence of it. In the vacuum of space, there is no medium for sound to travel. And on many rogue planets, if the atmosphere is thin or non-existent, sound would be minimal even at the surface. It would be a place of profound silence, deeper than anything experienced on Earth. Even if movement occurred beneath the surface, it would remain hidden, unheard. Another fascinating aspect is the potential for complex chemistry beneath the surface. In subsurface oceans or warm layers, chemical reactions could occur over long periods of time. Minerals interacting with water, heat driving slow transformations, creating environments that, while hidden, are not inactive. These processes unfold slowly, quietly, without interruption. And here is a deeply calming truth. Rogue planets are not in a hurry. They do not rush toward anything, nor do they move away with urgency. Their motion is steady, consistent, guided by the fundamental laws of physics. In a universe filled with dynamic systems and energetic events, rogue planets represent a kind of stillness, a long, uninterrupted journey through space. They are not anchored, not illuminated, yet they persist. Another thought gently emerges. These planets may outlive many stars. While stars burn through their fuel and eventually fade or explode, rogue planets, especially smaller rocky ones, can continue drifting long after their parent stars have disappeared. They are quiet survivors, carrying their existence forward through cosmic time. As you continue to relax, imagine one of these worlds, far from any star, moving slowly through the galaxy. Its surface cold and still, its interior quietly warm, its path unchanging. There is no rush, no noise, no expectation, only motion and time. And in that silence, there is a kind of peace, a reminder that even in the vast emptiness of space, existence continues gently, endlessly, without needing to be seen. Chapter 5. The Search for Habitable Worlds. As your thoughts continue to drift gently through the vast cosmic ocean, we now arrive at a question that has quietly followed humanity for centuries. A question that does not demand urgency, but invites calm curiosity. Are there worlds beyond Earth where life could exist? The first truth to settle into is this. When scientists speak of habitable planets, they are not necessarily speaking of places filled with life, but rather places where conditions might allow life to exist. It is a subtle distinction, but an important one. At the heart of this search lies a simple requirement: liquid water. On Earth, water is essential for all known forms of life. It acts as a solvent, a medium for chemical reactions, and a stabilizing presence in biological systems. Because of this, scientists often focus on finding planets where liquid water could exist on the surface. This leads us to another quiet truth: the concept of the habitable zone. The habitable zone is the region around a star where temperatures are just right, not too hot, not too cold, for liquid water to exist. If a planet is too close to its star, water evaporates. Too far, and it freezes. But within this delicate range, there is a possibility. It is sometimes called the Goldilocks zone, a place where conditions are just right. And yet, this idea, while useful, is only the beginning. Another truth slowly emerges. Being in the habitable zone does not guarantee habitability. A planet could sit perfectly within this region, yet still be completely inhospitable. Consider a planet with a thick atmosphere of carbon dioxide. Even at the right distance from its star, it could experience a runaway greenhouse effect, trapping heat and raising temperatures far beyond what liquid water can tolerate. Or imagine a planet with no atmosphere at all. Without atmospheric pressure, water cannot remain liquid. It either freezes or evaporates. Habitability is a balance. Another gentle truth is that stars themselves vary greatly. Our Sun is a relatively stable, middle-aged star, but many stars in the galaxy are smaller, cooler red dwarfs. These stars are far more common, and many of the potentially habitable planets discovered so far orbit them. However, red dwarfs can be unpredictable. They often emit powerful flares, bursts of radiation that can strip away a planet's atmosphere or alter its surface conditions. And yet, some planets may still endure. If a planet has a strong magnetic field or a thick atmosphere, it may be able to withstand these flares, maintaining stable conditions over time. It is a quiet resilience shaped by invisible forces. Another fascinating truth is that the habitable zone itself is not fixed. As a star ages, its brightness changes, causing the habitable zone to shift outward. A planet that is habitable today may not remain so forever, and a planet that is currently too cold may warm over time. Habitability is not static. It evolves. There are also planets that may be habitable beneath their surfaces. Even outside the traditional habitable zone, where surface temperatures are too low for liquid water, internal heat could maintain subsurface oceans. We see hints of this even in our own solar system, on moons like Europa and Enceladus, where oceans exist beneath thick layers of ice. If such conditions can exist here, they may also exist elsewhere on distant exoplanets. Another quiet truth is that size matters. A planet must be large enough to retain an atmosphere, but not so large that it becomes a gas giant. This places many potentially habitable worlds in the category of Earth-sized planets or super-Earths. These planets may have enough gravity to hold onto gases, maintain pressure, and support long-term stability. But again, size alone is not enough. Another factor is composition. A planet rich in volatile compounds like water and carbon dioxide may develop an atmosphere and climate system. Geological activity, such as volcanic eruptions, can release gases and shape the environment over time. Without such activity, a planet may become geologically inactive, losing its atmosphere and becoming barren. Another truth lies in the importance of a magnetic field. On Earth, our magnetic field protects us from solar wind, deflecting charged particles that could otherwise strip away our atmosphere. Without this protection, a planet's atmosphere may gradually erode, leaving its surface exposed. Mars, for example, is believed to have lost much of its atmosphere due to the absence of a strong magnetic field. So when scientists search for habitable exoplanets, they are not just looking for the right distance from a star, but a combination of many factors: atmosphere, size, composition, magnetic field, and more. It is a complex puzzle with many pieces. Another fascinating truth is that some planets may exist in what is called the habitable edge. These worlds are on the boundary of the habitable zone, where conditions are marginal, but still potentially stable under the right circumstances. On such planets, even small changes could shift the balance, turning a habitable world into an inhospitable one, or vice versa. It is a delicate equilibrium, constantly maintained, yet easily altered. There are also planets that orbit multiple stars, where the habitable zone may be more complex, shifting as the stars move relative to each other. These systems present unique challenges, but also new possibilities. And then, there is time. Another quiet truth is that life, at least as we understand it, requires time to develop. A planet may have the right conditions, but if those conditions do not persist long enough, life may never emerge. Stability over billions of years may be just as important as the conditions themselves. As you continue to relax, imagine these distant worlds, some orbiting quietly within their stars' habitable zones, others hovering on the edge, their conditions shifting slowly over time. They are not identical to Earth, but they share certain qualities, small overlaps that invite curiosity. And in the vastness of the galaxy, even a small overlap can mean a great deal, because among billions of stars and countless planets, there may be places where the conditions are just right and not perfectly, but enough. Enough for something to begin. As your thoughts continue to drift gently through the quiet search for distant, life-friendly worlds, we move deeper into the subtle ways scientists try to understand planets they cannot touch, cannot visit, and can only observe through faint traces of light. Another truth begins with how we study atmospheres, because an atmosphere is often the key to understanding whether a planet could support life. When a planet passes in front of its star, a small portion of the starlight filters through the planet's atmosphere before reaching us. Within that thin layer of light, there are clues. By analyzing this filtered light, scientists can detect specific molecules, tiny signatures that reveal the composition of the atmosphere. This technique allows us to identify gases like water vapor, carbon dioxide, methane, and oxygen. Each of these gases tells a different story. Water vapor suggests the presence of moisture, carbon dioxide hints at greenhouse warming, methane can come from geological or biological processes, and oxygen, on Earth, is closely linked to life. But here is a quiet and important truth. No single gas confirms the presence of life. Instead, scientists look for combinations, patterns, imbalances that are difficult to explain through non-biological processes alone. For example, the simultaneous presence of oxygen and methane in large amounts could suggest ongoing processes that replenish them, possibly biological in nature. It is not proof, but it is a signal worth listening to. Another gentle truth is that clouds can both reveal and conceal. Thick cloud layers may reflect light, making a planet easier to detect, but they can also obscure the atmosphere beneath, hiding important chemical signatures. Some planets may be wrapped in global cloud systems, making it difficult to see what lies below. Others may have clearer skies, offering a more direct glimpse into their atmospheric composition. This balance between clarity and concealment adds another layer of complexity to the search. Another fascinating truth is that temperature can be estimated from a distance. By observing how much heat a planet emits and how it interacts with the light of its star, scientists can approximate its surface or atmospheric temperature. This helps determine whether liquid water could exist, or whether the planet is too hot or too cold. But again, temperature alone is not enough. Another quiet realization is that planets with similar temperatures can have very different environments. Venus and Earth, for example, are similar in size and receive comparable amounts of sunlight, yet their surface conditions are vastly different. Venus is covered in thick clouds of sulfuric acid, with surface temperatures hot enough to melt lead, while Earth remains balanced and life-supporting. This reminds us that small differences over long periods of time can lead to dramatically different outcomes. Another truth lies in the concept of biosignatures, indicators that may suggest the presence of life. These include certain gases, chemical patterns, or even surface features that could be associated with biological activity. For instance, on Earth, plants reflect light in a specific way, creating what is known as the red edge in the light spectrum. Detecting similar patterns on distant planets could hint at vegetation, or at least something functionally similar. But interpreting these signals requires caution. Many processes can mimic biological signatures, and without direct observation, certainty remains just out of reach. Another gentle truth is that habitability does not mean comfort. Even if a planet supports life, it may not be a place humans could easily survive. Conditions could include high pressure, unusual atmospheric compositions, or extreme environments that are very different from Earth. Life, if it exists there, would likely be adapted to those specific conditions shaped by its environment over time. Another fascinating aspect is the role of planetary rotation. A planet that rotates slowly may experience long periods of daylight and darkness, affecting temperature distribution and atmospheric circulation. Faster rotation can create stronger winds, more dynamic weather systems, and a more even distribution of heat. These subtle differences influence how energy moves across the planet, shaping its climate in ways that are not immediately obvious. There is also the question of water distribution. Even if a planet has water, it may not be evenly spread. Some regions could be dry, others flooded, creating a patchwork of environments. This diversity can increase the chances of stable niches where life might develop, even if other areas are less favorable. Another truth emerges when we consider planetary age. Younger planets may still be undergoing intense geological activity, with unstable climates and frequent changes. Older planets may have settled into more stable conditions, but could also have cooled internally, reducing geological activity. There is a window of time where conditions may be most favorable, a balance between activity and stability. Another quiet realization is that our search is still in its early stages. While thousands of exoplanets have been discovered, only a fraction have been studied in detail, and even fewer have been analyzed for potential habitability. Each new telescope, each new mission, brings us closer to understanding these distant worlds. And yet, the universe remains vast and full of quiet uncertainty. There is also a growing effort to study smaller, Earth-sized planets which are more difficult to detect, but potentially more relevant to the search for life. Advances in technology are gradually making this possible, allowing us to observe finer details and detect subtler signals. Another gentle truth is that we may one day find a planet that appears strikingly similar to Earth in size, temperature, and atmospheric composition. But even then, confirming the presence of life will require careful study, patience, and perhaps new methods we have yet to develop. Discovery, in this sense, is a gradual process. As you continue to relax, imagine these distant worlds, each one quietly orbiting its star, carrying its own combination of conditions, its own balance of elements, its own potential. Some may be barren, silent, unchanged for billions of years. Others may be dynamic, evolving, shaped by forces both internal and external. And somewhere, perhaps, there is a world where the conditions align, not perfectly, but enough. Enough for chemistry to become complexity, for simplicity to become structure, and for something, however small, to begin. You do not need to know where it is, or when it might be found. It is enough to understand that the search itself is part of the story, a quiet, ongoing effort to understand our place in a universe filled with possibilities. And as your thoughts settle, you can rest within that idea that among countless stars and countless worlds, the conditions for life may not be unique, but part of a much larger and still unfolding cosmic pattern. Chapter 6. Atmospheres of Fire, Ice, and Glass. As your thoughts continue to drift softly through the vastness of distant worlds, we now move into something more subtle, yet deeply revealing. Not the surface of planets, not their size or orbit, but something that surrounds them quietly, shaping everything that happens above and below. Their atmospheres. The first truth to gently understand is this. A planet's atmosphere is not just a layer of gas. It is a living system, constantly moving, changing, and interacting with both the planet and its star. On Earth, our atmosphere gives us air to breathe, regulates temperature, and creates weather. But beyond Earth, atmospheres can become something far more unfamiliar. Some burn, some freeze, and some behave in ways that feel almost impossible. Let us begin with the hottest. There are exoplanets where the atmosphere is so intensely heated that molecules cannot remain stable for long. Temperatures can rise above 2,000 or even 3,000 degrees Celsius, enough to break apart most compounds into individual atoms. In these extreme conditions, the atmosphere becomes a dynamic mix of ionized gases, glowing faintly under constant stellar radiation. It is not a sky in the way we know it, but a shifting, heated envelope of energy and particles. Another quiet truth is that on some of these worlds, the atmosphere flows differently from Earth. Instead of vertical weather systems driven by sunlight heating the surface, many exoplanets, especially those that are tidally locked, experience powerful horizontal winds. Because one side always faces the star, it remains extremely hot, while the opposite side stays much cooler. This creates a constant temperature imbalance, driving winds from the hot side to the cold side at incredible speeds. These winds can reach thousands of kilometers per hour, carrying heat, particles, and clouds across the planet in a continuous loop. It is a world where the atmosphere never rests. Another fascinating truth is that clouds on these planets are not made of water. Instead, they can form from materials that would seem impossible in Earth's conditions. Silicates, iron, aluminum oxide, substances that we think of as rock or metal, can vaporize under extreme heat, rise into the atmosphere, and condense into clouds. These clouds may shimmer, reflect light, or absorb it, depending on their composition. And here is something quietly astonishing. On some planets, it may rain molten iron. In the upper atmosphere, iron vapor can cool slightly, condensing into liquid droplets. These droplets fall not as water, but as glowing metal, descending through layers of gas before evaporating again. It is a cycle similar to rain on Earth, but composed of entirely different elements. Another truth reveals itself when we consider colder worlds. Not all exoplanet atmospheres are heated to extremes. Some exist far from their stars, where temperatures drop so low that gases condense into clouds of ice or even snow-like particles. On these planets, clouds may be composed of methane ice, ammonia, or other frozen compounds. The sky could appear pale, hazy, or softly colored, depending on how light interacts with these particles. In such environments, the atmosphere may be calm, with slow-moving currents and gentle changes over time. Another gentle realization is that atmospheres can vary greatly in thickness. Some planets have dense, heavy atmospheres that create immense pressure at the surface. Others have thin atmospheres, barely present, offering little protection or insulation. This thickness determines how heat is retained, how weather forms, and how the surface interacts with space. A thick atmosphere can trap heat, creating stable temperatures, while a thin one allows heat to escape quickly, leading to extreme variations. Another fascinating truth is that some atmospheres glow, not because they are hot, but because they interact with stellar radiation. Charged particles from the star can collide with atmospheric gases, causing them to emit light. This is similar to the auroras on Earth, but on a much larger scale. Imagine a planet where the entire atmosphere shimmers faintly, glowing softly in response to its star's energy. It is a quiet, constant display, unseen by any observer, yet always present. Another truth lies in the chemical diversity of these atmospheres. Some are dominated by hydrogen and helium, others by carbon dioxide, methane, or even more complex molecules. The exact composition depends on the planet's formation, its distance from the star, and its evolutionary history. Over time, atmospheres can change. Gases may escape into space, react with the surface, or be replenished by volcanic activity. It is a slow, continuous transformation. There are also planets where the atmosphere is in a state of escape. Intense radiation from the star can heat the upper layers, causing gases to expand and drift away into space. This process can create extended atmospheres, stretching far beyond the planet itself, forming a kind of invisible halo. In some cases, this escaping gas forms a tail, trailing behind the planet as it orbits its star. Another quiet truth is that atmospheres can influence the color of a planet. Depending on the gases and particles present, a planet may appear blue, red, yellow, or even nearly black. These colors are not just visual details. They are clues, hints about what the atmosphere is made of, and how it behaves. Another fascinating realization is that we are beginning to map these atmospheres, even from vast distances. By observing how light changes as a planet orbits its star, scientists can infer temperature differences, wind patterns, and chemical composition. It is a delicate process, but it allows us to study worlds we cannot see directly. As you continue to relax, imagine these atmospheres, some burning with heat, others drifting in cold silence, all of them moving, changing, shaping the worlds they surround. They are not static layers, but dynamic systems, each one unique, each one part of a larger story. And in their quiet motion, they reveal that even something as simple as air can become something extraordinary when shaped by the vast and varied conditions of the universe. As your thoughts continue to drift through these distant and ever-changing skies, we move deeper into the quiet complexity of planetary atmospheres, where even the smallest variations can transform an entire world. Another gentle truth begins with layers. On Earth, our atmosphere is divided into layers like the troposphere and stratosphere, each with its own temperature and behavior. But on exoplanets, these layers can be far more extreme and far less predictable. Some atmospheres may have temperature inversions, where higher layers are hotter than lower ones. This can happen when certain gases absorb stellar radiation efficiently, heating the upper atmosphere while leaving the lower regions cooler. Creates a strange structure where warmth comes from above rather than below. Another fascinating truth is that some exoplanets may have atmospheres that are constantly being reshaped by their stars. On planets orbiting very close to their stars, radiation is not just a source of heat, it becomes a force of erosion. Ultraviolet and X-ray radiation can break apart molecules, ionize gases, and gradually strip the atmosphere away. Over time, this process can dramatically alter a planet's composition, transforming it from a thick, gas-rich world into something thinner, quieter, and more exposed. It is a slow unraveling, happening over millions or billions of years. Another quiet realization is that atmospheres can carry memory. The gases present today are often shaped by events that happened long ago. Volcanic eruptions, impacts, chemical reactions, and gradual loss to space. By studying an atmosphere, scientists can piece together a planet's history, like reading a story written in invisible ink. Every molecule has a past. There are also atmospheres that may be dominated by unfamiliar chemistry. On some planets, carbon may form complex chains, creating hazes that block light and give the sky a deep, muted color. These hazes can scatter light in unusual ways, making the planet appear dim or even featureless from a distance. Such atmospheres can hide what lies beneath, creating a world that is both present and concealed. Another truth emerges when we consider circulation patterns. On Earth, wind patterns are influenced by rotation, temperature differences, and the distribution of land and ocean. But on exoplanets, especially those without continents, circulation can take on entirely different forms. Some planets may have a single, dominant jet stream that encircles the entire globe. Others may have multiple layers of winds moving in different directions, creating a complex, shifting system. These patterns determine how heat is distributed, how clouds form, and how stable the atmosphere remains over time. Another fascinating truth is that some atmospheres may be partially transparent, allowing us to see deeper into the planet's structure. In such cases, observations can reveal temperature gradients and chemical variations at different depths. This gives us a kind of indirect view not of the surface, but of the layers beneath the visible sky. Another quiet realization is that atmospheres can act as shields. A thick atmosphere can protect a planet's surface from harmful radiation, absorb incoming energy, and maintain a stable environment. But it can also trap too much heat, leading to extreme greenhouse conditions. It is always a balance, protection and excess, stability and change. There are also planets where the atmosphere is in constant expansion. Under intense heat, gases can swell outward, creating extended envelopes that stretch far into space. These atmospheres may be so large that they blur the boundary between the planet and its surroundings. In some cases, the atmosphere becomes larger than the planet itself. Another truth lies in the role of gravity. Stronger gravity helps a planet retain heavier gases, creating denser atmospheres. Weaker gravity allows lighter gases to escape more easily, leading to thinner atmospheres. This relationship between gravity and atmosphere is subtle but essential. It determines whether a planet can hold onto its air or slowly lose it over time. Another fascinating aspect is the possibility of seasonal changes. On planets with tilted axes, similar to Earth, different regions may receive varying amounts of stellar energy throughout their orbit. This can create cycles, periods of warming and cooling, shifts in atmospheric composition, and changes in cloud cover. Even on distant worlds, there may be rhythms, slow, repeating patterns shaped by motion and light. Another quiet truth is that some atmospheres may be almost completely still. If temperature differences are minimal and rotation is slow, there may be very little movement. The sky could remain unchanged for long periods, with clouds barely shifting and winds almost absent. It would be a place of deep stillness, where time feels stretched and change is almost imperceptible. And then, there are atmospheres we have yet to fully understand. Despite all our observations, many exoplanet atmospheres remain mysterious. Signals are faint, interpretations uncertain, and models incomplete. Each new discovery adds detail, but also raises new questions. It is a process of gradual understanding, built on patience and careful observation. Another gentle realization is that atmospheres are not permanent. Over time, they can be lost, transformed, or replenished. A planet's atmosphere today may be very different from what it was in the past, and very different from what it will become. Change, even on a planetary scale, is constant. As you continue to relax, imagine these distant skies, some glowing with heat, others dim and cold, all of them shaped by forces both visible and unseen. They move quietly, carrying particles and energy, forming clouds, dispersing them, evolving slowly over time. And though we cannot stand beneath these skies or feel their winds, we can understand them, piece by piece, through the faint light that reaches us across space. In that light, there are stories, not spoken, but revealed one observation at a time. And as your thoughts settle, you can rest within that quiet understanding that even the air of distant worlds holds secrets waiting patiently to be discovered. Chapter 7. How we detect the invisible worlds. As your thoughts continue to drift softly through the quiet expanse of distant systems, we now turn toward something more subtle, more delicate, and quietly extraordinary. How do we even know they are there? The first truth to gently settle into is this: most exoplanets are never seen directly. They do not shine like stars. They do not glow brightly against the darkness. Instead, they remain hidden, lost in the overwhelming light of their parent stars. And yet, through patience, precision, and careful observation, we have found them. One of the most important methods is known as the transit method. This method relies on a quiet, repeating event. When a planet passes in front of its star, from our point of view, it blocks a tiny fraction of the star's light. This causes a slight dip in brightness, so small that it may only be a fraction of a percent. But with sensitive instruments, this dip can be measured. Imagine watching a distant candle and noticing that, at regular intervals, its light dims ever so slightly. You cannot see what is passing in front of it, but you know something is there. That is how many exoplanets reveal themselves. Another gentle truth is that this dimming must be consistent. A single dip in brightness is not enough. But if the same pattern repeats at regular intervals, it suggests a planet in orbit. By measuring how often the dip occurs, scientists can determine the planet's orbital period, how long it takes to complete one orbit. And by measuring how much light is blocked, they can estimate the planet's size. It is a quiet process of inference, building a picture from small, consistent signals. Another fascinating truth is that this method works best when the alignment is just right. The planet's orbit must pass directly between its star and Earth. If the orbit is tilted, even slightly, the planet may never transit from our perspective. This means there are many planets we cannot detect using this method, simply because of their orientation. And yet, even with this limitation, thousands have been found. Another key method is known as the radial velocity method, sometimes described as detecting a star's wobble. Planets do not simply orbit their stars. They also exert a gravitational pull on them. As a planet moves around its star, it causes the star to move slightly as well, shifting back and forth in a small, repeating motion. This motion affects the light emitted by the star. When the star moves toward us, its light shifts slightly toward the blue end of the spectrum. When it moves away, the light shifts toward red. These changes are incredibly small, but they can be measured with precise instruments. It is like listening to a distant sound and noticing a subtle change in pitch as something moves closer, then farther away. From this wobble, scientists can estimate the planet's mass and its distance from the star. Another quiet truth is that combining these two methods, transit and radial velocity, provides a more complete picture. One reveals size, the other reveals mass. Together, they allow us to calculate density, offering clues about the planet's composition. Is it rocky, like Earth, or gaseous, like Jupiter? All of this from light that has traveled across space. Another fascinating method is called direct imaging, though it is far more challenging. In this approach, astronomers attempt to capture actual images of exoplanets. But because stars are so bright, their light overwhelms anything nearby. To overcome this, special instruments block out the star's light, allowing the faint glow of nearby planets to become visible. Even then, only certain planets can be seen, usually large ones far from their stars, and still relatively young, emitting their own heat. The images are not detailed, but they are real, small points of light representing entire worlds. Another quiet truth is that time plays a crucial role in detection. Many methods require repeated observations, sometimes over months or years. Patterns must be confirmed, signals verified, and noise eliminated. It is a slow, patient process. There are also methods that rely on gravitational effects, such as microlensing. When a planet passes in front of a distant star, its gravity can bend the light from that star, briefly magnifying it. This effect is rare and unpredictable, but it allows us to detect planets that might otherwise remain hidden, including those far from their stars, or even rogue planets drifting alone. It is like noticing a brief flash in the distance and understanding that something unseen has passed by. Another fascinating truth is that each method has its strengths and its limitations. Some are better at finding large planets, others at detecting smaller ones. Some work best for close orbits, others for distant ones. No single method reveals everything. Instead, they work together, each contributing a piece to the larger picture. Another gentle realization is that we are constantly improving these techniques. New telescopes, more sensitive detectors, and advanced data analysis methods are allowing us to find planets that were once beyond our reach. Planets smaller than Earth, planets farther away, planets with subtle signals that would have been lost in the past. Each improvement opens a new window, revealing more of the universe. And here is something quietly profound. We are discovering these worlds without ever leaving Earth. Through light, through motion, through careful observation, we are mapping planets across vast distances, learning their properties, and imagining their nature. As you continue to relax, imagine this process. Scientists watching distant stars, recording tiny changes, waiting patiently for patterns to emerge. It is not loud or dramatic, but quiet, steady, and deeply focused. And in that quiet observation, entire worlds reveal themselves one signal at a time. As your thoughts continue to drift through the quiet precision of discovery, we move deeper into the subtle art of finding planets that cannot be seen, only understood. Another gentle truth begins with timing, because in astronomy, timing is everything. When scientists observe a star, they are not just looking at it once, but many times over long periods. Patterns must repeat, signals must align, and randomness must be ruled out. A single observation is never enough. Instead, it is the quiet repetition, the steady rhythm of data that confirms the presence of a planet. This patience is essential. Some planets take days to orbit their stars, others take years, and some may take decades. Detecting them requires a willingness to wait, to observe, and to trust that the pattern will reveal itself in time. Another fascinating truth is that light carries more information than we might expect. When we observe a star, we are not just measuring brightness, but also the spectrum of its light, the way it spreads into different wavelengths. Within this spectrum, tiny variations can indicate motion, composition, and even the presence of planets. These variations are incredibly subtle, often buried within noise, requiring advanced instruments and careful analysis to uncover. It is like listening for a whisper in a quiet room, where even the smallest disturbance can obscure the signal. Another quiet realization is that noise is always present. Stars themselves are not perfectly stable. They have spots, flares, and natural variations in brightness. These can mimic or mask the signals of planets, making detection more challenging. Distinguishing between stellar activity and planetary influence is one of the most delicate parts of exoplanet research. It requires not only data, but interpretation, experience, and sometimes a bit of intuition. Another truth lies in the concept of false positives. Sometimes what appears to be a planet turns out to be something else. A binary star system, an instrumental artifact, or a background object can create signals that resemble planetary transits or wobbles. Because of this, every potential discovery must be carefully verified, often using multiple methods or independent observations. It is a process of careful confirmation, ensuring that what we see is truly what we think it is. Another fascinating aspect is the role of space-based telescopes. Observatories placed above Earth's atmosphere, such as the Kepler Space Telescope and the James Webb Space Telescope, have transformed our ability to detect exoplanets. Without atmospheric interference, these telescopes can observe stars with greater clarity, detecting smaller dips in brightness and analyzing light with higher precision. The Kepler Space Telescope, in particular, spent years staring at a single patch of sky, monitoring over 150,000 stars, and discovering thousands of exoplanets. It did not move quickly or dramatically, but remained still, watching, waiting, recording. Another quiet truth is that modern missions continue this work, expanding our reach and refining our methods. The Transiting Exoplanet Survey satellite focuses on nearby stars, scanning almost the entire sky, searching for planets that are closer to Earth and easier to study in detail. This shift toward nearby systems allows for deeper analysis, including atmospheric studies and follow-up observations. Another fascinating method involves studying transit timing variations. In systems with multiple planets, the gravitational pull between planets can cause slight changes in the timing of their transits. Instead of passing in front of the star at perfectly regular intervals, they arrive slightly earlier or later. These variations can reveal the presence of additional planets, even those that do not transit themselves. It is like watching a clock and noticing that its ticks are not perfectly even, hinting at hidden influences behind the scenes. Another truth lies in the use of advanced algorithms and artificial intelligence. Modern astronomy generates vast amounts of data, far more than humans can analyze manually. Machine learning systems are now used to sift through this data, identifying patterns, filtering noise, and flagging potential planetary signals. These systems do not replace human judgment, but they enhance it, allowing scientists to focus on the most promising discoveries. It is a quiet collaboration between human insight and computational precision. Another gentle realization is that we are beginning to detect smaller and more Earth-like planets. In the early days, most discoveries were large gas giants, easier to detect due to their size and influence. But as technology improves, we are finding smaller planets, with weaker signals, closer to the size of Earth. These discoveries require greater sensitivity and more careful analysis, but they bring us closer to understanding worlds that may be more familiar. Another fascinating truth is that some methods are still in development. Future telescopes may use techniques like star shades, large structures that block starlight before it enters the telescope, allowing for clearer direct imaging of planets. Others may use interferometry, combining light from multiple telescopes to achieve higher resolution, revealing finer details. These methods are not yet widely implemented, but they represent the next step in our ability to explore distant worlds. Another quiet truth is that detection is only the beginning. Finding a planet is one thing, understanding it is another. Once a planet is detected, scientists continue to observe it, analyze its light, model its atmosphere, and refine their estimates. Each planet becomes a subject of ongoing study, revealing more over time. And yet, even with all this progress, there are limits. There are planets too small, too distant, or too faint to detect with current technology. There are signals too subtle, patterns too complex, and systems too distant. But these limits are not permanent. They are simply the boundaries of what we can see, for now. As you continue to relax, imagine this quiet process of discovery. Telescopes watching distant stars, data flowing in patterns slowly emerging. There is no rush, no urgency, only steady observation, careful analysis, and a deep curiosity about what lies beyond. And in that stillness, in that patience, entire worlds are revealed, not through direct sight, but through the gentle language of light, motion, and time. Chapter 8. The most extreme planets ever found. As your thoughts continue to drift deeper into the quiet vastness of distant systems, we now arrive at some of the most unusual and quietly astonishing worlds ever discovered. These are not gentle planets, nor familiar ones. They exist at the edges of what seems possible, shaped by extremes of heat, pressure, gravity, and motion. And yet, they are real. The first truth to settle into is this: the universe does not limit itself to Earth-like conditions. Instead, it explores every possibility, creating worlds that stretch the boundaries of imagination. Another fascinating truth is that some planets have highly eccentric orbits. Instead of moving in near-perfect circles, they follow elongated paths, bringing them very close to their star at one point and very far away at another. This creates dramatic changes in temperature over the course of a single orbit. A planet may experience intense heat during one phase and deep cold during another. It is a cycle of extremes, repeating over and over without pause. Another extreme lies in gravity itself. There are planets so massive that they sit on the boundary between planets and stars. These objects, sometimes called brown dwarfs or supermassive planets, have immense gravitational pull. Their atmospheres may be thick and turbulent, with pressure increasing rapidly toward the interior. These worlds blur the line between categories, challenging our definitions of what a planet truly is. Another quiet truth is that some planets may be made largely of carbon. Under the right conditions, carbon can form structures very different from those found on Earth. Some scientists have suggested the possibility of diamond planets, where high pressure transforms carbon into crystalline forms. While the details remain uncertain, the idea itself reflects the diversity of planetary composition. Another fascinating extreme is found in planets with powerful storms. On some gas giants, storms may rage continuously, driven by internal heat and rapid rotation. These storms can be larger than entire planets like Earth, lasting for years or even centuries. Winds may circle the planet at incredible speeds, shaping cloud patterns and atmospheric layers. And yet, from a distance, these storms appear as quiet swirls, patterns moving slowly across the surface. Another truth emerges when we consider planets with unusual orientations. Some exoplanets have orbits that are tilted at extreme angles relative to their star's rotation. Others may even orbit in the opposite direction, a phenomenon known as retrograde motion. These unusual alignments suggest complex formation histories, involving gravitational interactions and migrations. The universe, it seems, does not always follow a simple plan. Another quiet realization is that some planets may be stretched by tidal forces. When a planet orbits very close to its star, gravitational forces can distort its shape, pulling it into an elongated form. Instead of being perfectly spherical, the planet may appear slightly stretched with one side closer to the star than the other. This constant stretching and compressing can generate internal heat, adding another layer of complexity to the planet's environment. Another fascinating truth is that some planets reflect very little light, making them incredibly dark. Their atmospheres may absorb most incoming radiation, leaving them with a deep shadow-like appearance. Even when close to bright stars, they remain dim, almost invisible. It is a quiet kind of darkness shaped not by absence, but by absorption. As you continue to relax, imagine these extreme worlds, each one shaped by different forces, each one existing at the edge of what seems possible. They are not chaotic, but they are intense, balanced in their own way, following the same fundamental laws, yet expressing them in dramatically different forms. And in their quiet orbits, they remind us that the universe is not limited to the familiar, but extends far beyond, into realms of heat, pressure, and motion that continue to surprise us. As your thoughts continue to drift through these distant and extraordinary worlds, we move further into the quiet extremes that define them, where the universe seems to explore its most unusual possibilities, not with chaos, but with calm, consistent precision. Another gentle truth begins with brightness. While some planets are dark and absorbing, others are remarkably reflective. There are exoplanets with thick cloud layers composed of highly reflective materials, making them shine brightly in the light of their stars. These clouds can reflect a large portion of incoming radiation, giving the planet a pale, luminous appearance. But this brightness can be deceiving. Beneath those reflective clouds, temperatures may still be extremely high, or atmospheric conditions may be harsh and unstable. What appears calm and bright from a distance may hide a far more intense environment below. Another fascinating truth is that some planets are so close to their stars that their atmospheres are being actively pulled away. These are often called disintegrating planets. As they orbit, intense radiation and tidal forces strip material from their surfaces, creating long streams of dust and gas trailing behind them. These tails can stretch for vast distances, forming a faint, comet-like appearance. Over time, the planet gradually loses mass, becoming smaller and less stable, until it may eventually disappear entirely. It is a slow, quiet fading, happening over millions of years. Another extreme lies in the concept of ultra-low-density planets. Some exoplanets are so light for their size that they are often described as puffy. Their atmospheres are expanded, stretched outward by heat, making them much larger than expected. These planets can have densities lower than that of water, meaning they would float if placed in a sufficiently large ocean. It is a strange contrast, a world that appears large and dominant, yet is surprisingly light and diffuse. Another quiet truth is that some planets exist in extreme radiation environments. Orbiting very active stars, these planets are constantly exposed to high-energy particles and bursts of radiation. Their atmospheres may be ionized, their surfaces altered, and their overall structure influenced by continuous exposure. And yet, they persist, adapting to these conditions over time. Another fascinating realization is that some exoplanets may experience supersonic winds. Driven by extreme temperature differences and rapid rotation, winds on these planets can exceed the speed of sound. These winds move heat and material across the atmosphere, shaping cloud patterns and redistributing energy. It is a constant motion, fast, powerful, yet part of a stable system that continues without interruption. Another truth emerges when we consider planets with unusual compositions. Some worlds may contain large amounts of heavy elements, others may be dominated by lighter gases, and some may have compositions that challenge our current models. There are planets that appear to be rich in metals, others that are unusually poor in them. These differences provide clues about how and where the planets formed, and how they have evolved over time. Another quiet realization is that some planets may have surfaces unlike anything we can easily imagine. On certain lava worlds, the surface may not be solid or stable, but constantly shifting, with molten material flowing and cooling in cycles. On others, thick atmospheres may prevent us from seeing the surface at all, leaving it hidden beneath layers of gas and cloud. In some cases, the surface may be so compressed by gravity, or so altered by chemistry, that it behaves in ways that are difficult to visualize. Another fascinating truth is that some planets may have extreme day-night contrasts. On tidally locked worlds, the side facing the star can be intensely hot, while the opposite side remains extremely cold. The boundary between these regions, the terminator, may be a place of rapid change, where temperatures shift dramatically over relatively short distances. This creates a planet divided not by continents or oceans, but by light and darkness. Another truth lies in orbital resonance. In systems with multiple planets, gravitational interactions can lock planets into synchronized orbits. One planet may complete 2 orbits for every 1 orbit of another, creating a repeating pattern. This resonance stabilizes the system, but also introduces subtle variations in motion, adding complexity to the planetary dance. Another quiet realization is that some extreme planets may not remain extreme forever. Over time, orbits can change, atmospheres can evolve, and conditions can shift. A planet that is currently hot and volatile may cool, or one that is stable may become more dynamic. The universe is not fixed. It is always changing, even if those changes happen slowly. Another fascinating truth is that some exoplanets may be tilted at such angles that their poles receive more direct light than their equators. This creates unusual patterns of heating, with polar regions warmer than expected and equatorial regions cooler. It is a reversal of what we experience on Earth, and a reminder that even basic assumptions can be different elsewhere. Another quiet truth is that despite all these extremes, these planets are not chaotic. They follow consistent physical laws, they maintain orbits, and they exist in stable configurations over long periods of time. What appears extreme to us is simply another form of balance. As you continue to relax, imagine these worlds, each one defined by its own set of extremes, yet all moving quietly through space, following their paths without interruption. And in their quiet existence, they remind us that the boundaries of possibility are far wider than we once believed. Chapter 9. The possibility of life beyond Earth. As your thoughts continue to drift gently through the quiet expanse of distant worlds, we now arrive at one of the most timeless and softly compelling questions of all. Not rushed, not urgent, but always present. Could there be life beyond Earth? The first truth to settle into is simple, yet profound: we do not yet know. Despite all our discoveries, all our observations, and all our growing understanding of exoplanets, we have not confirmed life anywhere beyond our own planet. And yet, the possibility remains. Another gentle truth begins with what we mean by life. On Earth, life is based on carbon, uses water as a solvent, and relies on energy from the sun or chemical sources. These characteristics guide our search, shaping the way we look for life elsewhere. But it is important to remember, this is only one example. Life, if it exists elsewhere, may follow similar principles, or it may be different in ways we have not yet imagined. Still, we begin with what we know. Another quiet realization is that life on Earth appeared relatively early in the planet's history. Within a few 100 million years of Earth's formation, simple life had already begun to emerge. This suggests that, under the right conditions, life may not be an extremely rare event, but something that can arise when the environment allows. Another truth lies in the resilience of life. On Earth, life exists in places once thought impossible. Deep beneath the ocean, near hydrothermal vents, organisms thrive without sunlight, using chemical energy instead. In frozen environments, in acidic lakes, and even within rocks, life finds a way to persist. These extremophiles expand our understanding of where life can exist, showing that it does not require gentle or familiar conditions. It requires only stability and energy. Another fascinating truth is that some exoplanets may offer environments similar to those extreme habitats. Planets with subsurface oceans, thick atmospheres, or geothermal activity could provide the necessary conditions for life, even if their surfaces appear hostile. Life, if present, may not be visible from above, but hidden beneath layers, quietly sustained by internal processes. Another gentle truth is that the search for life often focuses on chemical signatures. As mentioned before, certain gases, like oxygen and methane, can indicate processes that are difficult to explain without biological activity. But interpreting these signals requires caution. Nature has many ways of producing similar effects. Volcanic activity, chemical reactions, and atmospheric processes can all mimic signs that might otherwise suggest life. Because of this, scientists look for combinations, patterns that persist over time, and signals that align with multiple lines of evidence. Another quiet realization is that life does not need to be complex to be significant. Even the simplest microbial life, single-celled organisms, would represent a profound discovery. It would mean that life is not unique to Earth, but part of a broader cosmic pattern. Complex life with intelligence and awareness is a much rarer possibility, requiring a long chain of stable conditions and evolutionary steps. But even simple life would change everything. Another truth lies in the role of energy. Life requires a source of energy to sustain itself. On Earth, this energy often comes from sunlight, but it can also come from chemical reactions, such as those found near hydrothermal vents. On other planets, energy sources may vary. Internal heat, tidal forces, or chemical gradients could all provide the necessary conditions. Life, if it exists, adapts to what is available. Another fascinating aspect is the concept of biospheres. A biosphere is the region of a planet where life exists, interacting with the environment, shaping and being shaped by it. On Earth, our biosphere extends from deep ocean trenches to high in the atmosphere. On other planets, biospheres may be limited to specific regions, perhaps beneath the surface, or within narrow zones where conditions are stable. These biospheres may be small, hidden, and difficult to detect, yet still active. Another quiet truth is that time plays a critical role. Life does not appear instantly. It develops gradually, over millions or billions of years. A planet may have suitable conditions, but if those conditions do not last long enough, life may never emerge. Stability, once again, becomes essential. Another realization is that we may already be observing planets that host life without knowing it. The signals we detect are subtle, and our interpretations are still developing. It is possible that among the thousands of known exoplanets, some already support life, quietly without drawing attention. We simply have not yet learned how to recognize it. Another gentle truth is that the search for life is not only scientific, but philosophical. It touches on questions of existence, uniqueness, and connection. If life exists elsewhere, it suggests that the processes that led to our existence are not isolated, but part of a broader pattern. It does not diminish Earth, but places it within a larger context. Another fascinating thought is that life elsewhere may not rely on oxygen at all. On Earth, oxygen is a byproduct of photosynthesis, but early life existed before oxygen became abundant. On other planets, life may use entirely different chemical pathways, based on available elements and conditions. This expands the range of environments where life might exist, beyond what we might initially expect. As you continue to relax, imagine these distant worlds, some with oceans hidden beneath ice, others with thick atmospheres, others orbiting quietly within their stars' habitable zones. On some of these worlds, there may be nothing, only silence. On others, there may be simple processes, chemistry slowly becoming more complex, structures forming, systems emerging. And perhaps, somewhere, there is life, not loud, not visible, but present, quietly existing, as it does here, shaped by its environment, sustained by energy, and evolving over time. And in that possibility, there is a kind of calm, a gentle understanding that life, wherever it may be, is part of the same universe, following the same quiet rules, unfolding in its own time. As your thoughts continue to drift gently through the quiet possibility of life beyond our world, we move deeper into the subtle ways scientists try to listen for it, not through voices or signals, but through patterns, chemistry, and quiet evidence carried by light. Another gentle truth begins with detection from a distance. Unlike exploring Earth, where life can be seen, touched, and studied directly, the search for life on exoplanets must rely on indirect clues. These clues are often faint, delicate, and open to interpretation. One of the most promising approaches involves studying a planet's atmosphere for biosignature gases, substances that, on Earth, are strongly linked to biological activity. Oxygen is one such gas. On our planet, it is continuously replenished by plants and microorganisms through photosynthesis. Without life, oxygen would gradually react with other elements and disappear. So, detecting oxygen in large amounts on another planet could be significant. But here is a quiet and important truth. Oxygen can also be produced without life, through processes like the breakdown of water molecules under intense ultraviolet radiation. This means that oxygen alone is not enough. Instead, scientists look for combinations, such as oxygen and methane existing together. These gases react with each other and would not persist simultaneously without a constant source replenishing them. If a similar pattern were detected on another planet, it could suggest the presence of widespread biological processes. But again, interpretation is delicate. Different planetary conditions could produce similar signals, and life elsewhere may not follow the same patterns as on Earth. Another quiet realization is that life may not be visible on the surface at all. On many exoplanets, especially those with harsh surface conditions, life, if it exists, may be hidden beneath layers of ice, rock, or ocean. Subsurface environments, shielded from radiation and temperature extremes, may provide stable conditions for life to persist. These hidden ecosystems would be difficult to detect from afar, leaving only subtle traces, if any. Another truth lies in the concept of chemical imbalance. A planet in chemical equilibrium, where all reactions have settled into a stable state, may be less likely to host active processes. But a planet with a persistent imbalance, where certain gases or compounds are continuously replenished, suggests ongoing activity. On Earth, life is a major contributor to such imbalance. Detecting similar patterns elsewhere could hint at something dynamic, something active, even if it is not immediately recognizable. Another fascinating aspect is the role of future telescopes. Instruments like the James Webb Space Telescope are already beginning to analyze the atmospheres of distant planets with unprecedented sensitivity. By observing in infrared wavelengths, these telescopes can detect subtle chemical signatures, even in faint, distant systems. And beyond this, future missions are being designed to go even further, capable of directly imaging Earth-sized planets and analyzing their atmospheres in greater detail. Each advancement brings us closer, not to certainty, but to clearer questions. Another gentle truth is that life may not announce itself. It may not produce strong signals or dramatic changes. Instead, it may exist quietly, subtly influencing its environment in ways that are difficult to distinguish from natural processes. The universe does not prioritize visibility. Life, if it exists elsewhere, may simply continue without the need to be seen. Another quiet realization is that intelligence, if it exists beyond Earth, is even more difficult to detect. Complex, technological civilizations would require not only life, but a long chain of stable conditions, evolution, and development. Even then, their signals may not reach us, or may not be recognizable. The absence of evidence is not evidence of absence. Another truth lies in patience. The search for life is not something that can be completed quickly. It requires decades, perhaps centuries, of observation, refinement, and understanding. Each new discovery adds a small piece, but the full picture remains incomplete. And that is part of the process. Another fascinating thought is that life, if it exists elsewhere, may not be rare, but simply difficult to detect. The galaxy is vast, containing hundreds of billions of stars, and likely even more planets. Even if life arises on only a small fraction of these worlds, the total number could still be significant. But distance, and the limitations of our current technology, make it challenging to confirm. Another gentle truth is that the search itself has value. Even without finding life, the process of exploration expands our understanding of planets' chemistry and the conditions that shape worlds. It teaches us more about Earth and about the delicate balance that allows life to exist here. Another quiet realization is that we are part of this story. The atoms that make up our bodies, the elements that form our planet, all originated in stars long before Earth existed. In that sense, we are already connected to the universe we are exploring. The search for life is also a search for understanding that connection. As you continue to relax, imagine these distant planets, some quiet and still, others dynamic and evolving, each one carrying its own set of conditions. On some, there may be nothing but rock and silence. On others, there may be oceans, atmospheres, and subtle chemical processes unfolding over time. And somewhere, perhaps, there is life. Not necessarily complex, not necessarily visible, but present, quietly existing, adapting, evolving, just as it has on Earth. And whether we find it soon or much later, or not at all, the possibility itself remains. A quiet, steady thought, drifting alongside the countless worlds that fill the universe. Chapter 10. The Future of Exoplanet Exploration. As your thoughts continue to drift softly through the vast and quiet universe, we now arrive at something gentle, something forward-looking, not rushed, not urgent, but steadily unfolding. The future, not as something distant or uncertain, but as a continuation of everything we have already begun. The first truth to settle into is this: we are still at the very beginning of exoplanet exploration. Only a few decades ago, we did not know for certain that planets existed beyond our solar system. Today, we have discovered thousands, each one adding to a growing understanding of how diverse and complex planetary systems can be. And yet, this is only the first layer. Another quiet truth is that our tools are improving, slowly, steadily, with each new generation of technology. Telescopes are becoming more sensitive, capable of detecting smaller changes in light, observing fainter stars, and analyzing more distant systems. Instruments are becoming more precise, allowing us to measure not just the presence of planets, but their atmospheres, temperatures, and compositions. Each improvement reveals more detail, like adjusting the focus on a distant scene. One of the most significant steps forward has been the launch of advanced space telescopes such as the James Webb Space Telescope. Designed to observe in infrared wavelengths, it allows scientists to study the atmospheres of exoplanets with greater clarity than ever before. By analyzing how light interacts with these atmospheres, it can detect molecules, measure temperature differences, and provide insights into conditions that were once beyond our reach. It does not travel to these planets, but it brings their details closer to us. Another gentle truth is that future missions are already being planned. New telescopes are being designed with the specific goal of finding Earth-like planets, worlds similar in size and temperature to our own. Some of these missions aim to directly image such planets, capturing faint light that has traveled across space. To achieve this, scientists are developing techniques to block out the overwhelming brightness of stars, allowing the much dimmer planets nearby to become visible. It is like creating artificial shadows, so that something hidden can finally be seen. Another fascinating truth is the concept of star shades. These are large, specially shaped structures that would travel alongside telescopes, positioning themselves between the telescope and a star, blocking its light before it even reaches the instrument. With the star's light removed, the faint glow of orbiting planets could be observed more clearly. It is a quiet and elegant solution, using shape and distance to reveal what was once invisible. Another truth lies in the possibility of mapping exoplanets. While we cannot yet see detailed images of their surfaces, future technologies may allow us to infer surface features, such as oceans, continents, or cloud patterns, based on changes in reflected light. As a planet rotates, different regions come into view, altering the light we detect. By analyzing these variations, scientists can begin to reconstruct a rough picture of the planet's surface. It is not direct sight, but a form of careful reconstruction, built from subtle changes over time. Another quiet realization is that we are beginning to focus more on nearby stars. While distant systems offer valuable information, closer stars provide opportunities for more detailed study. Planets orbiting nearby stars are easier to observe, allowing for repeated measurements and deeper analysis. This shift toward local exploration does not limit our understanding, but refines it, bringing clarity to specific systems. Another fascinating truth is that collaboration plays a key role in the future of exploration. No single telescope or mission can reveal everything. Instead, observations from multiple instruments are combined, each contributing different types of data. Ground-based telescopes, space-based observatories, and theoretical models all work together, creating a more complete picture. It is a quiet coordination, spanning countries, institutions, and years of effort. Another truth lies in the role of artificial intelligence and data analysis. As the volume of data increases, new methods are needed to process and interpret it. Machine learning systems can identify patterns, detect subtle signals, and assist in the discovery of new planets. But even with advanced tools, human understanding remains essential, guiding interpretation, asking questions, and refining conclusions. It is not a replacement, but an extension of our ability to observe. Another gentle realization is that future exploration may reveal unexpected types of planets. Just as early discoveries challenged our assumptions, future findings may introduce entirely new categories, worlds that do not fit into current models. The universe, it seems, is always ready to surprise us. Another fascinating truth is that we may one day detect clear signs of habitability, or even life, not through direct contact, but through unmistakable patterns in atmospheric chemistry, signals that cannot easily be explained by non-biological processes. Such a discovery would not be sudden or dramatic, but gradual, built on evidence, confirmed through repeated observation. A quiet confirmation, rather than a loud announcement. Another truth is that exploration does not always require travel. While the idea of visiting exoplanets is often imagined, the distances involved are immense. Even the closest stars are light years away, far beyond the reach of current spacecraft. And yet, through observation, we are already exploring them. Light becomes our messenger, carrying information across space, allowing us to study worlds without leaving our own. Another quiet realization is that this process takes time. Discoveries are made slowly, carefully, with attention to detail. Each new piece of information builds upon the last, forming a gradually expanding understanding of the universe. There is no need to rush. As you continue to relax, imagine the future of this exploration. Telescopes quietly observing, data flowing steadily, patterns emerging over time. There are no sudden movements, no urgency, only a continuous effort to understand what lies beyond. And in that steady progress, the universe reveals itself one small detail at a time. As your thoughts continue to drift gently forward, beyond what we know, into what is quietly unfolding, we arrive at the deeper horizon of exploration. Not a sudden leap, but a gradual expansion, like light spreading slowly across a distant sky. Another gentle truth begins with perspective. As we discover more exoplanets, our understanding of Earth subtly changes. What once felt like the center of everything now becomes one example among many, not less important, but part of a wider pattern. This shift is not unsettling, but calming. It reminds us that the universe is not empty, but filled with structure, variation, and quiet repetition. Another truth lies in the idea of comparison. As we gather more data about distant planets, we begin to compare them, not just individually, but collectively. Patterns start to emerge: common sizes, common orbital arrangements, recurring atmospheric features. These patterns help us understand how planetary systems form, how they evolve, and how they differ from our own. It is like listening to many voices and slowly recognizing a shared rhythm. Another fascinating truth is that future exploration may allow us to study exoplanet weather in real time. By observing changes in light over hours or days, scientists can track cloud movement, temperature shifts, and atmospheric dynamics. These observations are still in early stages, but they offer a glimpse into the daily behavior of distant worlds. Even across vast distances, motion can be seen. Another quiet realization is that we may one day identify truly Earth-like planets, not just in size or distance, but in a combination of factors: atmosphere, temperature, composition, and stability. Such a planet would not be identical to Earth, but it may share enough characteristics to feel familiar. Finding such a world would not change our place in the universe, but it would deepen our understanding of what is possible. Another truth is that the boundaries of detection will continue to expand. Planets that are currently too small, too faint, or too distant may become detectable with future instruments. Signals that are now lost in noise may become clear, patterns that are now uncertain may become defined. The limits we experience today are temporary. Another fascinating aspect is the possibility of detecting surface features indirectly. By studying how light reflects off a planet over time, scientists may be able to infer the presence of oceans, continents, or ice caps. Variations in brightness and color can reveal differences in surface composition, even without direct imaging. It is a quiet reconstruction, built from light and time. Another gentle truth is that exploration does not require certainty to be meaningful. Even when data is incomplete or interpretations are uncertain, each observation adds to our understanding. Science moves forward not by knowing everything, but by learning gradually, refining ideas, and adjusting models. Uncertainty is part of the process. Another quiet realization is that the search for life will continue alongside the search for planets. As detection methods improve and atmospheric analysis becomes more precise, the ability to identify potential biosignatures will grow. Each new observation brings us closer, not to immediate answers, but to clearer questions. And sometimes, better questions are more valuable than quick answers. Another truth lies in the idea of connection. The elements that form distant planets, the gases in their atmospheres, the processes that shape their surfaces, are all governed by the same physical laws that apply here. In that sense, these worlds are not separate from us, but part of the same system, the same universe. Another fascinating thought is that future generations will continue this exploration. What we begin now, others will expand upon. New technologies, new ideas, and new perspectives will build on the foundation we are creating. The story of exoplanets is not a single chapter, but an ongoing narrative, unfolding over time. Another gentle truth is that the universe does not reveal everything at once. It offers glimpses, fragments, hints that must be carefully interpreted. Each discovery is a piece of a much larger puzzle, one that may never be fully completed, but always enriched. And that is enough. Another quiet realization is that exploration itself is a form of understanding. By observing distant worlds, we learn not only about them, but about ourselves, our place, and the conditions that make our own planet unique. It is a reflection, seen through the lens of the cosmos. As you continue to relax, imagine the future unfolding slowly, telescopes observing quietly, data building gently, discoveries emerging one by one. There is no rush, no final destination, only a continuous journey of learning. And somewhere, among the countless stars, new worlds will continue to be found, studied, and understood, each one adding to the quiet story of the universe. And as your thoughts begin to settle, you can rest within that story, knowing that it continues, whether we are watching or simply imagining. A universe filled with worlds, moving silently, waiting patiently, and revealing themselves, one small detail at a time. As your thoughts slowly return, and the vastness of distant worlds begins to fade into a quiet stillness, remember this gentle truth. The universe is filled with countless planets, drifting, orbiting, glowing, each one following its own quiet path. Some are worlds of fire, some of ice, some hidden beneath oceans, and some wandering alone in the darkness. And yet, Among all that distance, all that silence, there is a kind of calm, because everything moves with purpose, with balance, with time. You don't need to understand it all tonight. You've already traveled far, beyond stars, beyond light, into a universe filled with quiet wonders. So now allow yourself to rest. Let the distant planets continue their silent motion. Let the stars glow softly in the background, and let your mind drift gently into sleep. Good night.